All right. Wanted to go through the difference between using the indefinite integral to solve a problem like this and kind of some of the, I guess, parallels that we're drawing when we use definite integrals. Okay, so I'm going to work through the indefinite integral first and maybe draw a couple of pictures and stuff like that so we can point to what's going on when we actually use this fundamental theorem of calculus on this side to solve a similar problem. Okay, so if I've got the derivative 2x and I want to find first f of x, I'm just going to go and say f of x is equal to the integral of 2x dx. And I'm just going to kind of view these as my parentheses there, right? And say that's asking me to do the power rule of the inside there. So I'm going to add 1, multiply by the reciprocal, which gives me x squared. But I don't really know what height that x squared is at. So I've got to put a constant with it. So the picture of that, what I have at this point, okay, is I know what the shape of my curve looks like. I just don't know how high it sits, right? So I don't know if it's this parabola that looks like an x squared, a version of x squared. I don't know if it's this one or any of the other ones that I could draw that look like x squared, right? The c value, when I go and find that, is going to allow me to figure out what the particular solution is or the specific version of x squared that we're looking at, okay? And to find that, I think everybody kind of knows, I use this reference point, okay? So let's go use that reference point. So if f of 2 is equal to 5, that means that 5 is equal to my x squared. So this is an f of x here, right? So if it's f of 2 there is equal to 5, when I put 2 in, I can go and find my c. So c is going to equal 1 here. Right? And so f of x is equal to x squared plus 1. Super simple example, but it's showing the concept, right? So now I know which x squared it is. It's this one right here that's 1 high, right? So here, let's get rid of that other arrow because it's kind of showing us that. Let's get rid of this. Okay, the actual curve that I'm looking for is the one that has a height of 1, right? And now if I want to finish the problem off, it says find f of 2. I don't want that. Let's find f of 3 instead. Okay, it's going to be different. It's going to be different than the one that's than the one that we gave already. We already know that's 5, right? So let's get rid of this. And let's find f of 3 instead, right? Okay, so I would go and plug 3 in. Okay, so I'm looking at 3 over here someplace. And what do I get out? I'm going to get 3 squared plus 1 is equal to 10. Okay, so up at this height on my particular curve, I'm going to get a height of 10. Okay, so that's what it looks like when we don't have the limits of integration, but they do kind of give us that reference point, and we use the plus c to find the particular solution of our f of x. Okay. All right, so let's use the definite integral to solve the same problem. Okay, so we're using our fundamental theorem of calculus here to go ahead and find that same value, f of 3. So we know the answer. When I'm finished whatever process we've got going here, I better get 10 when I get that value of f of 3, right? But we're just going to use our definite integral to do it, okay? So I think this is kind of what was bugging people a little bit. Values for f, I'm finding from here, right? So if I go and isolate for f of b there, okay, so I'm going to take this, I'm going to keep this on one side of the equation by itself. I'm just going to add f of a to the other side. Does that look good? Okay, I think that's pretty self-explanatory. Okay, but we're kind of using that idea of area. So this integral means the area underneath our derivative 2x from a to b. Okay, so what is this a and b? Well, the b is the value that I want, right? I'm looking for f of 3. Okay, so it's the x value that I want to kind of finish measuring my area to. Okay, and our reference point up here, our f of 2 is equal to 5, is supplying where I'm starting to measure that area from and how much I'm starting to measure that area from. It's kind of filling in, and it's kind of letting us know, it's kind of like we're skipping this plus c step, right? And we're going straight from here, straight to the value. So we're not really actually ever finding the particular solution. It's already kind of getting kind of passed over because we already know a reference point. It's kind of the beauty of the fundamental theorem of calculus here, that we don't have to go and do those extra steps. So as long as you know that I'm starting at what x, 2, and the value that I'm starting at when I'm at that 2 is 5, I'm going to add the area that's under the curve. Well, actually, here, let's just go straight away and call that 2x, right? Okay, our derivative of f dx. Okay, so I'm going to find the area from 2 to 3 under this curve, and I'm going to add it to 5, and that's going to give me my value of f at 3, which should equal 10. So I guess if I drew a graph of that, let's do it down here. Okay, if I drew a graph of what's actually going on here, it would look something like this. All right, I've got 2x, right, and the area from 2 to 3 that I'm accumulating, right, in here is going to get added to the starting point. Like this is like where what I guess value I'm starting at when I'm at 2, and then the area from 2 to 3, the integral is going to take care of for me, so I can add it to that 5 and get me my 10. All right, so well, let's just do it. This isn't really that tough now. So f of 3 is equal to 5 plus, and then the antiderivative of this we kind of figured was x squared, right? But now I'm taking that from 2 to 3. Okay, so this is equal to 5 plus, and then I'm going to dump 3 into x squared, which gives me 9, minus, I'm going to plug 2 into x squared, sorry, which is going to give me 4, and then looky here, I've got 5 plus 5 is equal to 10. All right, so we kind of, well, when I'm using this kind of start plus method to find a value of the function when I've been given the derivative, okay, I'm kind of skipping over this whole plus c part and finding the particular solution and going straight to what my answer is. So hopefully that, so here my f of 3, if I'm going to draw this like a cartoon, I guess, is going to equal the 5, the place where I started, plus the area that's under the curve in between 2 and 3 and the x-axis, and yeah, that ends up giving me the 10 that I want in the end. I really hope that helps. It's like the only way that we can make this question tougher, like you get it over and over and over again, whether the derivative that you have is a function, this is a really simple one, 2x, whether it's one of those pictures of a derivative that you're ending up with, this concept is the same for all of them. So yeah, just watch that a couple of times and work your way through a couple of examples, and you can maybe come back to this really simple example just to kind of sort yourself out and where you're at and what you're doing. So hope that helps.